In this lesson, we'll talk about logarithmic functions and some applications. Recall from the previous lesson that any function b to the x, any exponential function like that, is one-to-one. So, since it's one-to-one, it should have an inverse function. This inverse to exponential function b to the x will be called logarithmic function and will be denoted log with base b of x. So it's a logarithm with base b from x. X is the input, b is the base, log is the name of the function. Obviously the base is the same as the base of the exponential function that the log is reversing. So the base of the log is exactly the same as the base of the exponential function in order to be the inverse of it. How do we define log with base b from x? Well, first of all, b has to be bigger than 0. That's the same condition as for exponential function b to the x. Also, b should not be equal to 1, because as you remember, this would give us a degenerated case where exponential function would actually be a constant function. And the constant function, which is horizontal line, can't be reversed because it would become a vertical line, which is not a function. So we have to have a b different than 1. Also, we need to assume that the inputs are bigger than 0. And why? Well, since logarithm is an inverse to exponential, therefore the domain of logarithm will be the same as the range of exponential. But as we remember, the exponential function looked somehow like that. Therefore, the range of it was all positive numbers. So we should expect that the domain of logarithmic function will also be all positive numbers. Now, the formal definition of logarithmic function is just by using the inverse property. So logarithm with base b from x is such a y that the base b to this y is equal to x. Notice that the y is the exponent, so sometimes we are thinking of log as exponents. Again, logarithm with base b from x is such an exponent y that if we raise the base to the y, we get back our input x. So we can remember this in a circle like that. B to the y equals x. That's how you translate logarithm from x. Another way around, if our equation is given in exponential form like that, b to the y is equal to x, remember that that exponent represents exactly the logarithm of x. So we can remember as before, in kind of circular order, if we take log b from x, that will give us the exponent y. So here we have if and only if statement, and we need to be able to fluently convert from the logarithmic form to the exponential form, or from exponential to logarithmic. So here we have again explanation that log with base b of x is such an exponent y that b raised to the y gives the original x. Let's notice some properties. Since these two functions, the exponential and logarithmic with the same basis, are inverses to each other, when we compose them, we're supposed to end up with identity. So if we composed f of g of x, and g is the exponential b to the x, and f is log applied to it, so it's log with base b from b to the x, that should give us identity, but identity means that x goes on to x. Therefore, we end up with the first rule, that log with base b from b to the x, it's equal to x. You can think of it like kind of log with base b cancels the exponential base b and leaves the x by itself. As long as we have the same basis, these two functions annihilate each other, and we end up with just x. Similarly, we can compose the two functions the other way around. First apply logarithm and then apply exponential function. So our expression becomes b to the exponent, which is log with base b from x. Again, b cancels this log b, and you end up with just x. Which means we have second rule to remember, b to the log b from x equals to x. Okay, let's develop a couple more properties of log. Log base b from 1. How much this can be equal to? From the definition, the number that we are looking for should be such that b raised to this number will give us 1. Well, b to what exponent gives us 1? It must be 0. Anything to 0 is equal to 1. So log with base b, no matter what the b is actually equal to 0. And some other explanation could be, I could rewrite 1 as b to the 0. And then using this first property, log with the same base from the b to the 0 really cancels each other and we end up with 0. So yes, this is indeed the property and it's good to remember it. Log with any base from 1 is equal to 0. Okay, what about log with base b from b? Well, this is even easier because b is b to the 1. So when we cancel log with base b with the base of the exponential function, what's left is just 1. We follow the first property as before. In logarithms, we usually use two types of bases. Those are the most commonly used bases. Either base 10, and then we write log without mentioning the base. If you see something written like log x with no base at all, we assume that the base is 10. So that really means the same as log with base 10 of x, and this is called common logarithm. The other important base is base e. Remember, that was also important base for the exponential function. And in this case, the logarithm has a special name. It's called natural logarithm, and the abbreviation will be ln. So in short, you can call it ln rather than log. So ln really means log with base e. Now let's practice on a couple examples. Change the form of the given equation from logarithmic to exponential, or the other way around. So here we have equation in logarithmic form. This is equivalent to, and remember, let's go encircle this to this equals that. So this is equivalent to saying that 2 to the x equals 8. At this time, we're not asked to solve the equation, just to change the form. However, if we would like to predict what the x should be, well, since 8 is the same as 2 to the 3, and on the other side we have 2 to the x, it's easy to see that x should be equal to 3. So this is actually equivalent to saying that x equals 3. Why? Because the exponential function is 1 to 1. So if the values of this function at point x and at point 3 are equal, therefore the inputs must be equal. That's why we have equivalency here. And second question, again, we can translate this equation into exponential form by following base to the exponent equals the input. So 5 to the 3 equals x, which gives us the value of x. X is 5 to the 3, which is 125. So even though we haven't been asked for solving it, but as you see, changing the logarithmic form to exponential form helps us to find the value of x. Here we have exponential form. We need to change it to logarithmic form. So again, using the circular method, log with base x of 32 should be equal to 5. So let's record this. Log with base x of 32 equals to 5. And if we wonder what the x is, you're thinking, what to the 5 is 32? Actually, we know that 32 is 2 to the 5, right? So on that side, we have x to the 5, therefore the x must be equal to 2. This one, if you wonder what the x is, you can come up with this by yourself, similarly as before. But to comply with the request of the question, to change this to the logarithmic form, we should start with base 2, so log with base 2 of 16 equals x. That's how you resolve it. So the x is already solved. The x is equal log with base 2 from 16. But how much is that? If we think of 16, that it's really 2 to the 4, and on that side we had 2 to the x. Therefore, we know that this x is really equal to 4. So we know that this expression is actually equal to 4. It's good to keep this in mind. That's an exponent that 2 needs to be raised to in order to get 16. So that's another way of evaluating logs in your mind. Okay, in the next example we have ln. That means the base is e. Therefore, if I translate this to the exponential form, I have e to the negative 1 equals x. So that naturally solves for x. X is the same as 1 over e. And finally, here the x is already solved for, but still we need to change it to logarithmic form. How this would look like? Well, start with the base, so it's log with base 10. I don't need to mention 10 because that's a common logarithm of x is equal negative 2. That's the equivalent logarithmic form of the given exponential equation. Okay, so after you practice a little bit of this motion, let's try to evaluate expressions with particular numbers. Log with base 7 from 1. How can I see 1 as base 7 to something? For example, I can see this as log with base 7 from 7 to the 0 because that's 1. And then I can use the rule from the previous slide that you cancel the log and the base 7 and you end up with 0. So that's just 0. Log with base x from x. Again, the log and the exponent have the same basis, so they cancel each other and you end up with just 2. So that's nice. Here it's 2 to the log with base 2 from 17. Well, again, they cancel each other and you end up with 17. In the following example, we still have base 3, and this is something connected with base 3. But in order to cancel the log with exponential function with base 3, well, I need to have this expression as an exponent of 3. So let's change this 5th degree root of 3 as 3 to the 1/5. And then we are able to cancel log with the base 3, leaving us with 1/5. The next question, we have 3 times, and then we can take care of what's ln of e to the negative 10. Ln has a base e, so it cancels this exponential base e, and we end up with just negative 10. So overall, we have negative 30. And the next question is a little bit harder here because we can't really cancel these inverse functions 4 to something and log of something because of this 2 that disturbs us. So how can we get rid of this 2? Well, we can change the order of this multiplication. Since multiplication is commutative, I can take 4 to the log first and then take it to the 2, because when you take power to the power, you multiply exponents, so it's the same. Now, since these two functions are inverses to each other, we're allowed to reduce them, and we end up with just 5. However, the square still stays, so altogether is 25. So please analyze this question again by yourself so you can fully understand. You can't really get rid of 4 and log 4 if something is in between. Let's look at properties of a function of log with base b. So log with base b is the blue graph. For example, of this graph, it is inverse to the exponential function 2 to the x. And if the base is fractional, for example, here log with base 1/2 of x is the inverse to the exponential function 1/2 to the x. In both cases, when you look at blue graph, the domain is all positive numbers. So domain of log, any log, is from 0 to infinity. The range, though, can be any real number because this graph can rise without band. Sooner or later, it can reach any value that we wish. Similarly here, this graph is approaching y-axis really quickly, but it grows as far as we want to. So the range is all real numbers. And that's what we expected because the exponential function had domain all real numbers and the range positive numbers. The other important property of logarithmic function is that it has x-intercept exactly at the point 1. No matter what the base is, the x-intercept is exactly at point 1. And as you see, we have no y-intercept. Actually, y will be our asymptote. Since the logarithmic function is the image in symmetry in the diagonal of the exponential function, an exponential function always had a point, for example here 1, 2, generally 1b, then the logarithmic function will include point b1, in this case 2, 1, in that case 1/2, 1, and generally any b1. So these 2 points are on the graph for sure. Next, since this is inverse to exponential function which was 1-to-1, therefore logs are also 1-to-1. That means that the statement that log with base b from some n is equal to the logs of b from some m, we can actually get rid of those logs and say, therefore the inputs are equal. So if the values of the function are equal, then the inputs are equal. And obviously otherwise as well, if the inputs are equal, then the values are equal as well, because those are functions. So this implication is because logs are functions, but that implication is because logs are 1-to-1. As we mentioned before, we also have vertical asymptote, which is y-axis, with the equation x equals 0. So log with any base has a y-axis as its asymptote. If b is bigger than 1, for example, as on the first graph, then the function is increasing. It is increasing from the left to the right. So if we choose 2 points, any 2 points on the x-axis, one lower than the other, then the values are in the same order. The value at n is lower than the value at m. So the inequalities are preserved. Also, sticking with the same graph, if x's are approaching 0 from positive side, that means if I'm getting closer to 0 from the positive side, then the values are running away towards negative infinity. So function goes to negative infinity as long as x's are closer and closer to 0 from the positive side. Obviously they can't approach from the negative side because the negative numbers are not in domain. And function goes towards infinity if the x's are going towards positive infinity as well. So if the x's are increasing, the function is increasing without bound towards infinity. Now let's look at the example of the graph of any log with base between 0 and 1. Here we have base 1/2. Such function is decreasing. It's always going down. So if we choose 2 points, as before, any n and m in such order, n is smaller than m, then the value of logarithm at n is higher than the value of logarithm at m. So the inequalities reverse. That's important to remember. For bases bigger than 1, the inequalities are preserved. For bases between 0 and 1, the inequalities will be reversed when you apply log to both sides of inequality. And similar feature as before, as soon as we approach x from the positive side, what's going on with the graph? It's running away towards positive infinity. So we have f of x goes towards infinity as long as x is approaching 0 from positive side. Also, if x is approaching infinity, then the graph is approaching negative infinity, going down. Well, let's graph some functions involving logarithms by using transformations of the basic logarithmic graph. Okay, so to reach this graph, I should start with log with base 2 from x. We already know this graph. It comes through the 1, 0. It is rising, and it has 2, 1 on it. So the graph looks somehow like this. Now to get g of x, which is our log with base 2 from x minus 3 plus 1, we apply translation by the vector. We move the x 3 to the right, so it's 3, and 1 up, so it's 1. How this translation affects the asymptote, which was normally y-axis? Well, 3 to the right means that the asymptote will actually be moved to the position 3, at 3. And 1 up, well, the asymptote stays at the same place, but it is coming through the 3. So we're ready to move the graph. This point is moving 3 to the right and 1 up. It becomes here, and that point 3 to the right, 1 up over there. And we have an asymptote, so we volunteer a shape like this. So this is g of x. Okay, let's graph the second function. This time we start with ln x, then we want to graph negative ln x, and finally add 3. So from here to there, we need to apply symmetry in x-axis, because every value will go into opposite value. So we have flip over the x-axis. And from here to there, translation by adding 3 to the y value, so it's 0, 3. Okay, start as before by drawing ln x, so it comes through 1, 0, and the next point will be like 2.71 approximately here, and we have asymptote at y-axis, so the graph looks somehow like this. The next one, let's draw it in green. Flip over the x-axis. That means this point becomes here, that point is stationary, and we still have y-axis as an asymptote. So the graph looks somehow like this. And finally, in red, we're adding 3. So the asymptote will be at the same place. This point 1, 0 becomes 3. 2.7 negative 1 will become 2.7 plus 2. And volunteer a shape, so somehow like that. Okay, so the function h is the red graph. And a couple more graphs. P of x. Again, we start with log with base 2 of x, and then we apply the negative in front of the x, which is symmetry in y-axis. And finally, put the minus in front of the log. So we have symmetry in x-axis. But if you have symmetry in y and symmetry in x, this can be replaced as one symmetry, which is called central symmetry in O. So symmetry in one point. Okay, let's graph the first function in blue. Log with base 2. So it comes through 2 points, 1, 0 and 2, 1. And looks somehow like that. And then maybe we can apply symmetry in the origin and graph the final graph already. So symmetry in origin, this point becomes here, and that point go to the other side of the origin with the same distance. It will land over there. Now, the vertical asymptote, when flipped over the origin, is still the same vertical asymptote. However, the direction will actually be reversed. So in the original function, the points are growing towards the top right corner. In the flipped function, the points will grow towards the bottom left corner. And here we approach the asymptote. So that would be the function p. And the last example, let's start with log with base 1/2 of x. And then the next step will be already our s of x, which is log base 1/2 from x plus 4, which means we need to apply translation by the vector -4, 0. Okay, let's graph log 1/2. 1/2 means we still have point 1, 0, but the other point is 1/2, 1. It is diminishing function, going somehow like this. We can check one more point at 2. Well, 1/2 to what exponent is 2? It seems to be -1. So that will be another point to go through. So the graph goes somehow like that. Therefore, the final function, move everything 4 steps to the left. So this important point goes on to -3, 0, and that one here, and this one over there. The asymptote will also be moved 4 steps to the left. So it will be here. This is important to draw the asymptote because otherwise you don't know how to shape the graph. Goes somehow like that. Okay, that's your S of x. How do we find domains of functions involving logs or lns? Well, we need to remember that any logarithm, no matter what the base, have to have positive input. So in the first case, our input is x squared minus 9, and this has to be bigger than 0. So we need to solve this condition to find the domain. How do we do that? Well, we can bring the 9 to the other side and apply square root on both sides. That would mean that absolute value of x is bigger than 3. Okay, so how do we solve this kind of inequality? I'm looking for x's that are farther than 3 steps from 0. Okay, I can picture it out on the number line. If this is, for example, 0, I need to go more than 3 steps either way from 0. So either from 3 up or from -3 down without the endpoints, because it's strongly bigger than 0. Okay, therefore I'm ready to give the answer for the domain. Domain is, and read what you see on the diagram, from -infinity up to -3, or the union from 3 to the infinity. Second question, how to find the domain of ln of a root of something? Again, we want to have input strictly positive. Therefore, my radicand must be strictly positive. So 2x minus 5 must be positive. That's easy to solve. This is bigger than 5/2. Therefore, our domain of f, equals from 5/2 up to infinity. In next example, again, our input must be positive. So x plus 5 over x must be bigger than 0. But this is a rational inequality, so we actually need to consider two cases. When x plus 5 changes its sign, that happens at -5, and when x changes its sign, that happens at 0. So make a table of signs. That will be -5, that will be 0 on the number line, and the result, so x plus 5 changes its sign at -5. It is negative to the left and positive to the right. X changes its sign at 0, negative to the left, positive to the right. Therefore, the overall answer, when you have a quotient of two negatives, you end up with positive answer. This is negative and this is positive. Okay, I'm ready to give the final answer for the domain of f. The input is positive from -infinity up to -5, and I can't take -5 because this will become 0, and 0 is not allowed under ln, and also from 0 to infinity. So -infinity to -5, union 0 to infinity. The last example, what is domain of this function? Again, my input must be bigger than 0. But this is a square of something, so it's always bigger equal 0. Therefore, the only dangerous point is when this expression is actually equal to 0. So my x has to be different than 1. It can't be equal to 0. Anything else will be fine because it's squared. Therefore, it will be really positive. Okay, therefore my domain is all real numbers, but not number 1. That's the only number that has to be restricted from domain of f. And as a last, we have quite interesting application problem. We know that the number of digits n in the expansion of b to the x, where b and x are any positive integers, is given by the formula And in this formula, we use the greatest integer function, this double bracket. So to find out the number of digits in the expansion of this b to the x number, it's enough to take greatest integer of x, the exponent, times log with base 10 of b, take greatest integer of this, and add 1. So, that's interesting formula, especially for very large numbers, when we are really unable to even calculate, but we can still predict how many digits will this be. Okay, we know that 2 to the 10 is 1024. 2 to the 10 has 4 digits then. Well, verify that this formula really works. So, the x is the exponent, which is 10, times log b. b is 2, so it's log 2. Take the greatest integer of this value and add 1. So our n equals, when you use your calculator, plug it in 10 times log, so push the button log, not ln, of 2, you end up with approximately 3.01 and some other digits here, but that's not important for greatest integer, and then plus 1. So greatest integer of this number is really 3. 3 plus 1 is 4. Yes, it checks. Yes, indeed, 2 to the 10 has 4 digits. Then using this formula, find the number of digits in 3 to the 200. Okay, so what should we do? The number of digits is greatest integer of the exponent, which is 200, times log of the base, 3, and then add 1. Okay, when you calculate this using your calculator, it turns out to be approximately 95 point something, 0.4 and something else. Okay, plus 1. That means that I have 95 here plus 1, so it's really 96. And in this case, you can actually plug it in 3 to the 200 to your calculator, and you will end up with something that's written in scientific notation. You can see on the screen 2.6 and some other digits times 10 to the 95. So since the decimal is here and we have 95 more digits, plus this 1 digit in front is really 96 digits. In the next question, we are asked to find out the number of digits in 2012 to 2012. Obviously, this question was developed at year 2012, but let's do it. The number of digits is 2012 times log 2012, greatest integer plus 1. Okay, let's use our calculator. That turns out to be 6646.89, well, we can round it to 0.9, plus 1, which really is this greatest integer cuts off no matter how high is this ending, but still smaller than the next integer. So we end up with 6646 plus 1, which is 6647 altogether. You may want to change this number to the present year and evaluate the expression for the present year. And the last question asks us to find the number of digits in 9 to the 9 to the 9. Well, in order to do that, we actually need to know what is the number 9 to the 9. So first change this to 9 to the and 9 to the 9 end up to be 387420489, and then apply our formula. So the number of digits in this number is greatest integer of the exponent, which is 387420489, times log of 9, and then plus 1. After your calculation, you should end up with 369693100. That's the number of digits in this big number.